Okay, so good afternoon, everyone. I'm Crisia, and I'm helping Adriana in this series of quantum matter seminars. I hope you are enjoying it as much as we are. We have been trying to bring talks in both theory and experiments in quantum matter physics. And if you have suggestions, you can send it in your website or send us an email. All of them are very welcome. Well, today we have the honor to receive Professor Erez Berg from Weizmann Institute, who is going to talk about new physics in Moire flat bands. Just before I give him the comment, I would just remind you that if you have questions, Erez will stop at some points during his talk, and then we will unmute you. You will be muted during all the part in which he's going to speak. And then you can do your questions, or if you prefer, you can type them into the chat box here in Zoom, and then we can read it for you. So with that, I think we are all set to start. Thank you very much, Erez, for accepting your invitation. It's a pleasure to have you here today. So now the word is all yours.
Okay, thank you very much, Crisia and Adrienne, for organizing this seminar series and giving me the opportunity to speak here. I'm going to talk about physics of flat bands in Moire materials, and I'll touch upon a few topics. Here are my collaborators on these works. And just to set the background, I'd like to start from this nice quote from Bhaskaran. As you probably all heard, in the last couple of years, a little bit more, there have been a series of new systems that have been studied experimentally, where you in a 2D material, basically atomically thin material, you create a superlattice size of 10 nanometers or so, and you basically create a new material with extremely flat bands. So it started with twisted bilayer graphene, which was predicted 10 years ago and discovered and realized by Eva Andre and collaborators who did STM, and a couple of years ago at MIT, where they found that the system actually exhibits a host of strongly correlated phenomenon. And by now, that's not the only system of this class. So there's also a double, a bilayer on bilayer with a relative twist in between them, which also exhibits flat bands. Mentioned the system a little bit in the following. There's trilayer on HBN. There are even TMD materials that have were a superlattice and also exhibit flat bands and extremely strong correlations. Okay, so it's really become a rich field with several different systems and very rich phenomenology. And coming from sort of a quantum material strongly correlated perspective, this is really an exciting system. And I think there are various reasons for that. Let me just try to highlight a few. So it gives us an unusual tunability that we're not used to from bulk materials. So here's a system where we can essentially tune the ratio between the interaction and the bandwidth, if you like. Okay, so by tuning a parameter, for instance, the angle between the two layers and therefore the size of a unit cell, we can actually tune U over W over an extremely large range. That's not something we're used to from bulk quantum materials. We have new degrees of freedom. So if, for instance, in graphene, we have interplay between valley and spin degrees of freedom. We have band topology. So kind of the interface between the band topology and interaction effects like superconductivity and other strong correlation effects is probably playing an important role in these systems. And that's something that people realized over, I think, the last couple of years. And finally, there are new probes that are complementary in some sense to what we can use in bulk material. So some things are not easy to do in these kind of systems. It's an atomically thin system, so it's hard to do bulk measurements like specific heat. that you can do in bulk materials. On the other hand, there are new probes that are really using the fact that it's a 2D system. So starting with, you can change the density continuously, and you can also measure quantities that are not easy to measure in bulk materials. And one of them is the electronic compressibility, for instance. And if I have time, maybe I'll touch upon very interesting measurements of the compressibility done here at the Weizmann Institute. And we'll see if I actually get to that. Right, so that's roughly my plan. So I'm going to talk about a few topics. So first, I'll talk about superconductivity in flat bands and what's special in this kind of regime, and what we can say in terms of simple models. I'll talk about spin triplet superconductors. So there's an interesting, very intriguing possibility that some of these systems exhibit triplet superconductivity, and what special properties that might have related to the topology of the order parameter space. And finally, if I have time, which I most likely won't, but I'll touch upon experiments measuring the electronic compressibility in twisted bilayer graphene, which I think are telling us something very interesting about the system. And yeah, I apologize if I won't get to the third part, but yeah, please, if you have any questions during the talk, please raise your hand or write in the chat. I'll try to pause at some points and see if there are any questions. Okay, so the first part about superconductivity in flat bands, this was done with my postdoc, Johannes Hoffmann at Weizmann, and with Debanjan Chowdhury from Cornell. Okay, and you can look it up in this preprint over here. Okay, so the question here is what happens if we use this tunability that these kind of systems provide us, and we really try to reduce, given some interaction strength, we really try to reduce the bandwidth. Okay, so clearly we're going to enhance the role of correlations. And in particular, you can ask, suppose we can really tune the bandwidth all the way to 0. So we can really make, go to the extreme flat band limit and fixing the interaction strength. And for the sake of this discussion, I'm going to think about attractive interaction. So think about the negative, the magnitude of U is fixed. Its sign is always negative. Okay, so think about phonons or something. And can you get superconductivity in this kind of extremely correlated limit? Okay, and very often what we're used to is that if we take this extreme correlated limit, if we take the bandwidth to 0, TC would actually go to 0. And the reason TC would go to 0 is that the phase ordering scale, which is the phase stiffness, would go to 0. It would be proportional basically to the bandwidth, and therefore TC is not determined by the pairing scale, which would remain finite. It would be limited by the phase ordering scale, phase coherence scale, and that would go to 0. And a very classic example of this is the negative U-Hubbard model, where this would be the phase diagram. This is TC as a function of U, okay, but for a fixed bandwidth or fixed hopping on some lattice in 2 or 3D. Okay, so if the interaction strength is very small, we have basically a BCS theory that works well, and we know that the pairing scale would set TC, and TC would follow this functional form. It would be exponentially suppressed at small u. But once the interaction exceeds some scale that is determined by the bandwidth, okay, what would start happening is that the pairing scale sort of keeps going up as you increase the interaction more and more, but eventually the phase ordering scale would be set by this scale, which is of order t squared over u, or w squared over u. Okay, so that would start going down. And there's a very nice paper by Skalatar and Teresa Paiva, who I noticed is actually here, interestingly. What you get is that the maximum TC you can attain for a fixed bandwidth is basically when u is off the order of the bandwidth. Okay, and if you optimize TC, you would get that since there are no other parameters in the problem, you would get that TC is somewhere of the order of the bandwidth. There's no other scale then, okay, once you optimized over U. And it turns out from a quantum Monte Carlo calculations, it turns out that the maximum TC you get in a 2D square lattice is this number times W. Okay, so it's some dimensionless number. It happens to be quite small, but okay, that's just a number. Okay, so now this kind of idea that generally you cannot get a TC which is bigger than some number times the bandwidth was kind of formalized in a not very nice recent paper by Moire, Renderia and company, where they actually proved a bound, an upper bound on TC, written in terms of the bandwidth. Okay, and the idea is very simple. You basically use the F-sum rule on the optical conductivity. Okay, so you write the current operator, and you can express that in terms of the hopping of some tight binding model. So you get that the integral over all frequencies of sigma of omega, the real part of the optical conductivity, would be some number times the bandwidth. Okay, and you can show, it's not hard to show, that this the spectral weight bounds the superfluid density in the superconductor at 0 temperature. Okay, and in 2D, that would also, by the BKT relation, that would also bound TC from above. Okay, but there's an important caveat to this. Let's see, why is this, isn't this advancing? Okay, here we go. So this upper bound, okay, so this upper bound would tell you clearly that if you take the bandwidth literally to 0, TC has to go to 0. Okay, but there's an important caveat in this derivation, which is it's assumed that the interactions depend only on density. Okay, so basically that means in particular, when you take the bandwidth to 0, the current operator is also 0. Okay, so the current doesn't get any contribution from the interaction itself. Now, this bound is valid quite generally. Okay, now let's assume we have indeed some density dependent interaction. But if you think about the situation like in twisted graphene, where you have a flat isolated band with W, which is separated by more dispersive bands. Okay, so then to really apply this criterion literally, you have to integrate over sigma of omega over all frequencies. And they would include also the dispersive bands. Okay, so you really have to take this integral up to infinity, basically to integrate over all the electrons, including interband transitions, contributions to sigma of omega. Okay, and that would give you a bound which is correct, but clearly not very useful. Okay, so clearly if the chemical potential somewhere within this flat band, you don't really care about what's going on in these higher bands, but this bound, as it's formalized, as it's formulated, tells you that you have to integrate over everything. Now, the alternative is you can project the Hamiltonian onto the active band, okay, but then you need to project the current operator as well. If the wave functions of this active band are not completely localized, when you project the interactions onto the flat band, just as projecting the interaction onto a Landau level in a quantum Hall problem, okay, you know that these interactions become more complicated, and in particular, they depend not only on density. So then this is a possible way around this bound. Okay, so if the wave functions of this spanning this band are extended in space, basically if they're overlap in space, if in particular the Wannier wave functions of this band are not tightly localized, then this bound actually doesn't have to be obeyed with the bandwidth of the active band. Okay, so this leads to a kind of an intriguing idea that if you have extended Wannier functions spanning the active band, for instance, if these are topological bands, you know that you actually cannot find a localized Wannier basis at all. Then actually what you'll get is that even in the limit where the bandwidth goes to 0, the single particle kinetic energy goes to 0, the current operator doesn't go to 0. It actually is of the order of the interaction strength. And then a similar argument to the argument by Mohit would tell you that TC should actually scale like the interaction U. Okay, so why does it scale like the interaction U? Simply because there's no other scale in the problem. We took the bandwidth scale to 0. The interaction is the only scale in the problem. So if the system is superconducting, then it actually has to have a TC which is proportional to U. Okay, so that's the basic reasoning. And if this is the case, then we should have a we should have a phase diagram that looks like this. So this is again TC as a function of U. This is the bandwidth scale, and suppose the bandwidth is very small of the active band. So for when the interaction is much smaller than the bandwidth, again BCS theory is obeyed. But when the interaction is larger, then TC should become linear in U. It should grow linear in U. And how much can it grow? Of course, it cannot grow indefinitely. At some point, U would become bigger than the gap to the next band, and then we'll have to evaluate things again. Okay, so can we get superconductivity in this limit? Okay, so this argument is very solid, but of course this is a very strongly correlated system then, and we have to worry about other competing states. Does the system favor some kind of charge ordering instead of superconducting, or phase separates, or does something else intervene, or can we really get into this regime where TC is proportional to U? So that's the question I'd like to address. Okay, so maybe this is a good point to just pause for a moment and ask if there are any questions, just in terms of the problem I set up to solve. Okay, so right, so what we did is we've formulated a specific model which we can solve, where we can examine some of these questions. I'd like to define the model for you and show you some results. Okay, so here's the model. We have a tight binding model on a 2D square lattice, and the hopping parameters are chosen such that for each spin we have two churn bands. One band with churn number +1 and the other band with churn number -1. And the hoppings are chosen such that the problem has a time reversal symmetry. Okay, simply the hoppings for spin down are the complex conjugates of the hoppings for spin up. Okay, such that overall there's time reversal symmetry. This is some kind of spin orbit coupling, if you like. Okay, so it's a little bit like the quantum spinel effect. Okay, so this is the model. It has nearest neighbor and second neighbor hoppings with some phase factors. And here's the band structure that you get. Okay, so this model was actually written down by Newport et al. And the interesting thing about this model, okay, so the lower band for spin up has churn number, say, +1, and the upper band has churn number -1. The interesting thing is that you see that the bandwidth is relatively small, maybe a fifth, compared to the band gap between these two bands. Okay, but we really want to study what happens if we take the limit where the bandwidth goes to 0. So it turns out that if you modify this model slightly, you add a second neighbor diagonal hopping. Okay, so fifth neighbor hopping on the lattice. Okay, so you add this term T5. It turns out you can make this lower band really extremely flat without changing its wave functions at all. Okay, so this band is still a churn band, but now the ratio between the bandwidth and the band gap is almost 100. Okay, so now it's really in the extreme limit where the lower band is very, very flat. Okay, and so that's our band structure. That's a single particle dispersion, and we add to this a local negative Hubbard U. Okay, so a local attractive interaction, and ask what's the ground state of the system, and what's the phase diagram of the system. And luckily, this model doesn't suffer from the sign problem. Okay, so this is a strongly correlated regime. We don't a priori expect mean field theory to work so well, but we can solve the model numerically exactly using quantum Monte Carlo. Okay, which is what we did, this is what the phase diagram looks like. Okay, so it turns out that, as stated, the model actually is an S-wave superconductor. So the ground state is an S-wave superconductor, and this is Tc as a function of U for these two parameter sets that I've shown you before. Okay, so one is for the more dispersive band, where the ratio between the bandwidth and the band gap is about a fifth, and the dashed line is for the more flat band. Okay, so this is where the band is extremely flat. So you see that Tc rises rapidly with the coupling U. And the interesting thing is that for the case of the extremely flat band, indeed it is very linear as a function of U. So this is an indication that this is indeed the essentially the zero bandwidth limit. So, and nevertheless, the system is superconducting. Effectively, the only energy scale in the system is U. So U is up to 2 in these units of the hopping, the nearest neighbor hopping. The band gap in the same units is 4. Okay, so it's not all that small compared to the U is. It's not all that small compared to the band gap. And nevertheless, up to this value of U, Tc is very linear. Now, moreover, you see that if you increase the bandwidth, Tc actually goes up. So it looks like Tc in this regime is still limited by the phase coherence scale. The phase stiffness doesn't go to 0 even when the bandwidth goes to 0. Okay, and that's because of the fact that the wave function of the band is not completely localizable. But if you increase the bandwidth, the phase stiffness presumably goes up, and therefore Tc goes up. Okay, so now when we establish that this model is indeed superconducting, we can ask about its properties. So for instance, how does the transition from the normal state to the superconducting state occur? Okay, so clearly this is very non-BCS. And it turns out that in this flat band regime, there's a very large pseudogap regime above DC, where there's pairing with no phase coherence. And that's sort of what happens. We can probe that, for instance, by looking at the spin susceptibility of this model as a function of temperature. Okay, so that's shown by these circles. Okay, so this is chi SZ, that's the spin susceptibility. As a function of temperature, the dashed lines, the empty circles and dashed line is the more flat band. Okay, so this is what the spin susceptibility looks like. And you see that it starts getting suppressed quite a bit above Tc, which is here. Okay, so this is an indication that a gap opens in the spin sector quite far above Tc. So this is kind of very non-BCS-like. So this is the picture. It's kind of a preformed pair picture, if you like. The bound states start forming well above Tc, and the pairs become phase coherent only at a much lower temperature. You see that in the more dispersive case, which is this solid line in filled circles, the suppression of the spin susceptibility starts only slightly above DC. Okay, so there's a much smaller pseudo gap-like regime. And what's shown here in green is the orbital susceptibility. Okay, so this is, if you like, the onset of diamagnetic response, where this thing dives and crosses 0 is where a diamagnetism onsets. And again, in the flat band regime, you see that happens quite a bit above TC. Okay, so this is a sign, again, of fluctuating superconductivity that starts before you actually get to TC. Okay, so this is the red curves here are the onset of pseudo gap. We define as the position of the maximum in spin susceptibility, okay, just as an operational definition, okay, and compare that to TC in the two cases, in the more dispersive and the more flat band, and you see that indeed you have this broad pseudo gap regime with uncondensed pairs. Okay, now what about competing orders? So is there any other type of order which is nearby to superconductivity? So it turns out that there is actually very tight competition in this model. Okay, the competitor is phase separation. So it turns out that superconductivity in this model wins really by a small margin to phase separation. Phase separation is very close. So here are the inverses of the superconducting susceptibility chi delta and the charge susceptibility chi n. Okay, so again, the solid lines are the more dispersive band, the dashed lines are the more flat band. So you see that This is the inverse susceptibility. So it going to 0 means that the susceptibility diverges. That's the transition. So the superconducting susceptibility is the triangles. So the inverse goes down, the susceptibility diverges, and this is about TC. Okay, but you see that the charge susceptibility, which is circles, is only slightly above, which means that it's only slightly lower. Okay, and eventually it saturates close to TC. Okay, but it is enhanced by a very large factor as you lower temperature. Now, actually, if we perturb the model slightly, for instance, if we add a small nearest neighbor attractive interaction, which we can still do without causing a sun problem, we can actually drive this model to be to phase separate. Okay, so if we just add a small nearest neighbor attractive interaction, which is 10% of the on-site U, now the circles, which are the inverse of the charge susceptibility, actually reach 0 first. Okay, and the model phase separates and TC goes to 0. So just a 10% perturbation makes TC collapse to 0. So what's the cause of this very close competition between superconductivity and phase separation? So it turns out that there's a very simple reason that we learned after doing this simulation. Okay, so it turns out that if you project everything to the flat band, which is justified in the limit where the band is exactly flat and the interaction is much smaller than the band gap, then there's an emergent SU2 symmetry that relates the charge in the superconducting sectors. Okay, so in the limit where the band is exactly flat and the interaction is very small, these two sectors become exactly degenerate, and we're kind of approaching that then. So that's why the two sectors are nearly degenerate. This was actually pointed out in this paper by Sebi Huber and company. Okay, so that's what I wanted to say about superconductivity in flat bands. So yeah, so it looks like it's possible. And the main competitor, at least in this model, is phase separation, but probably it's possible to have other competing states in other models. And let me, before I move to another topic, let me pause for questions.
So we have a question by Erez. Yes.
Hi, Erez. So is there a generalization of your argument for topological bands with trivial churn invariance?
Yeah, yes. So right. So that's a good point. I believe, even though we start from a model with churn bands, I believe that the topology is actually not essential here. This is something we're actually we want to demonstrate now explicitly. But what's really important is simply that the Wannier functions of the band are not tightly localized. They're not just on site. So any band that has Wannier functions that are not completely localized would probably show similar phenomenology. Maybe the numbers would be different, but this is something we're looking at now.
Is it the difference between exponential and non-exponential, or is it a difference between?
I think it's a quantitative difference. I think that you can get similar phenomenon even if the Wannier functions are exponentially localized, but they're just big compared to the lattice site. I think you would get similar phenomenology, I believe, but yeah, we haven't checked that yet.
Similar phenomenology in the sense that TC is linear in U. It remains linear in U?
Yes, exactly. Yeah, precisely.
Okay, thanks.
I have two more questions. Daniel, I will unmute you.
Yeah, okay. You compared this superconductivity with phase separation. That's charge susceptibility at Q equals 0. What about possible competition? What about possible competition with something like charge density wave or Wigner crystallization of local pairs?
Yeah.
Final Q.
So yeah, it's a good question. We checked that. So within this model, the charge susceptibility is maximum at Q equals 0. Okay, so the phase separation tendency is stronger than any charge ordering intensity at finite Q. Now, of course, if this is sort of because we don't have long-range Coulomb interactions. If we had long-range Coulomb interactions, we would get instead any possible instability would be at the finite Q instead of Q equals 0, right? But here we just have an on-site interaction.
Usually in the order of T² over U, there is appear something like effective repulsion, which works in principle in favor of
that's right. Yes. Yeah. Absolutely. So that mechanism is not the dominant mechanism here. It turns out. Okay. So in this flat band limit, that mechanism doesn't dominate. Yeah. We actually expected some kind of charge density waves. And first, we were surprised to see phase separation, but it turns out that's what happens.
Okay. Thank you.
Now, Eagle has a
question. There's a question by Eagle.
Hi, Erez. I have a question about, I mean, you introduce or you get non-zero churn numbers compared to the standard model by introducing longer range hopping in the model.
Right.
Did you check what happens as you continuously take that next nearest neighbor hopping to 0?
So no, we didn't check. Presumably what would happen is that the first thing that would happen is that the bands would no longer be flat. So the flat band condition here is finely tuned. So if you start changing the second neighbor hopping, even before you would lose the churn number, just the bands would broaden. Okay, so to some degree, I mean, we looked at the beginning of this process, what happens if the bands become broader, but we didn't go all the way.
Okay, thank you.
All right. So now I'd like to go on. Okay, so I'd like to talk about order parameter topology and dissipation in a spin triplet spin polarized superconductor. This is work done with my postdoc Eyal Kornfeld at Weizmann and with my partner in Copenhagen. This work was posted recently. Okay, so I'd like to speculate. Okay, this is the speculation that stands behind this, but at the end I'm going to study a well-defined model that doesn't rely specifically on this speculation, but I think it's an interesting hypothesis. The hypothesis is that twisted bilayer graphene and its relatives are a good place to look for triplet superconductivity. Okay, so that's what we'd like to find. It's not been totally established yet, but hopefully maybe it will be. Okay, so what we'd like to do is basically to find a solid state analog of the only really good, well-established triplet superfluid that we have, which is helium-3. So this beautiful system of helium-3 atoms, which have this very rich phase diagram as a function of pressure and temperature, and there's several different superfluid phases. All of them are spin triplet, and that's very, very well established. Okay, and the question is, why aren't there such beautiful established solid state examples? And it turns out to be extremely difficult to find such examples. Okay, there are some materials that are believed to be triplet superconductors, but we still don't know absolutely. And also these examples are very, very rare. Okay, we know of hundreds of singlet superconductors and very few candidate triplet superconductors. The question is why? And I think I remember that, but I'd like to try to list some of the reasons. Okay, so first of all, triplet superconductivity requires strong electronic correlations. Okay, in weakly correlated materials with attractive interactions, phonons, you get singlet superconductivity. It helps to have nearby ferromagnetism, and as you know, ferromagnetism and superconductivity usually don't live very well together, but ferromagnetic fluctuations is exactly what you need in order to mediate triplet superconductivity. Moreover, these systems have to be extremely clean because even non-magnetic disorder would be pair breaking in triplet superconductor or actually any unconventional superconductor. Okay, and these reasons are presumably why it's so hard to find triplet superconductivity in quantum materials. Okay, so now I'd like to argue that twisted graphene is kind of maybe an ideal system to try to remedy all these difficulties. Okay, so definitely there's strong electronic correlations by taking this flat band limit. That's exactly what you get. There's nearby ferromagnetism, so that's pretty well established by now. Okay, in twisted graphene, there's this, among other experiments, there's this recent experiment by Shachalilani's group at the Weizmann Institute, where they measured the derivative of the chemical potential as a function of in-plane field, which is a direct measurement of the magnetization, the spin magnetization. Okay, and this is this red curve. This is dm/dn, a derivative of magnetization with respect to density as a function of density. And you see close to nu equals 1, there's this huge peak in dm/dn. So it looks like a spontaneous magnetization close to nu equals 1. This is a ferromagnet. Okay, so and there are other experiments, some of which I'll mention, that show ferromagnetism. And we know that this ferromagnetism lives at least not very far from superconductivity in the phase diagram. Now, these systems in some sense are actually quite clean. Okay, and there's a subtlety there. There is disorder, but it's mostly angle disorder and long wavelength disorder. Okay, so I'd like to argue that in some sense these systems are clean, so it looks like the ideal candidate. Okay, and so that's sort of a very general argument. Now, intriguingly, okay, these systems, unlike many solid state materials, also have very, very low spin orbit coupling because it's carbon-based systems. So you think about ferromagnetism and superconductivity living nearby. The ferromagnetism is really O3 ferromagnetism. It's free to rotate in all directions. And that leads to the possibility that if you have triplet superconductivity, the order parameter and the ferromagnetism might intertwine in an interesting way. And that's exactly what I'd like to pursue. Okay, now, interestingly, about a year ago, there has been a proposal, an experimental proposal, that a particular twisted graphene system is actually a triplet superconductor. Okay, and this is a very interesting system. It's two double layers of graphene, each one in Bernal stacking, non-twisted, but with a small twist angle with respect to each other. Okay, so each one of these is a bilayer on its own, so it's 4 layers overall, and with a small twist angle in between. Okay, and this system is interesting because it has actually, in addition to the twist angle, it has another very useful knob, which is a perpendicular electric field. So it turns out that the electric field perpendicular to the system also controls the bandwidth, and you can tune the bands to be extremely narrow, either as a function of angle or as a function of perpendicular electric field. Okay, so that's been figured out by several groups, more or less at the same time. Okay, and some of the phenomenology looks very similar to twisted bilayer graphene, not double. Okay, so in particular, there is some sort of correlated insulator phases that appear close to integer fillings. At half filling, it was found experimentally that the gap of this correlated insulator state increases linearly with in-plane field. Okay, so this is an indication of a ferromagnet, because if you have a polarized ferromagnet, you have polarized bands, and as a function of Semen, the filled band would go down in energy and the empty band would go up linearly. Okay, so it looks like there's ferromagnetism, spin ferromagnetism in the system. Now, most interestingly, there has been a proposal by Philip Kim's group that this system is close to half filling. If you change the density away from the correlated insulator, the system is actually a superconductor. And so what they see is that the resistance drops dramatically if you go away from half filling. Okay, you go away from the insulator, the resistance drops essentially to 0 as far as they can measure. Now, this claim is still controversial. Okay, it's still not entirely clear that this is what's going on. Okay, so they as of a few weeks ago, they still believed it's true, but there's there are more experiments going on. Okay, so to really establish this, more work would be needed. But let's assume for a moment that this is correct. Okay, so now most intriguingly, what they found is that the onset temperature of this drop in resistance. Okay, so this is the phase diagram of the system, temperature and in-plane magnetic field. And you see here the onset of the resistance drop in white, and what they interpret as the Kosteles-Taulis superconducting transition in black. And you see that it actually increases linearly as a function of in-plane magnetic field for small fields. And there's actually a cusp as a function of field at zero field. Eventually, if the field becomes big enough, it starts dropping. Okay, so TC goes up as a function of field. That's very, very unusual for a superconductor. And basically, the only way to get that is in triplet superconductor. Basically, triplet pairs can gain condensation energy in the presence of a Zeeman field. Okay, so this was the initial interpretation. Okay, so modulo the caveat about superconductivity. This is a very, very intriguing possibility. Okay, and this motivated us to think about triplet superconductors in these kinds of systems. Okay, so let me remind you a little bit about triplet superconductivity, which maybe you saw. Okay, so the order parameter of a triplet superconductor very generally involves also the spin. Okay, so the Cooper pair has total spin 1. So to specify the state of the Cooper pair, you have to specify not only the phase of the order parameter, but also the spin. Okay, and there's kind of a canonical way to parameterize the order parameter of a triplet superconductor, which is using the so-called D vector, which is defined in this way. Okay, so that's related to the spin polarization of the Cooper pair. Okay, it's a complex vector, so it's a complex order parameter, but it's a complex vector which specifies the direction of the spin. So these are the real and the imaginary parts of this D vector that I'll denote by D1 and D2. Okay, and the relative magnitude and relative direction of D1 and D2 determine the state of the triplet Cooper pair. Okay, so it can be m equals 1 triplet, m equals 0 triplet, and so forth. Okay, and that's all encoded in this relative direction and magnitude of D1 and D2. I'm going to focus on a particular kind of triplet superconductor in this talk, okay, which is the fully spin polarized superconductor. And that's kind of a natural state if you're in the vicinity of a ferromagnet. Okay, so you would say one spin direction condenses first. So at least close to TC, you would be in this fully spin polarized superconducting state where only spins, spin up and spin up along a certain quantization direction are actually condensed. Okay, and in terms of the D vector, this is the way to parameterize such an order parameter. The magnitude of D1 and D2 are equal, and their direction is perpendicular. Okay, so the direction of spin polarization of the Cooper pair is D1 cross D2. So this is the way to visualize it. Okay, so there's D1 and D2, which are two vectors, to take them to be unit vectors of equal magnitude and right angle to each other. And the direction of the cross product D1 cross D2 is M. That's the spin polarization of the Cooper pair. Okay, so if this is along Z, spin up is paired with spin up. Okay, so that's the order parameter we'll consider. There are other types of triplet order parameters that are possible. Okay, there are different phases, but we'll focus on this phase, which is particularly interesting. Okay, so the interesting thing to note is that if you neglect spin-orbit coupling, which is presumably extremely small in these systems, the order parameter space is SO3. So to specify completely the configuration of the order parameter, you have to specify this frame, which means that you have to specify basically an orthogonal matrix in SO3. Okay, so now in such a system, in principle, TC in 2 dimensions is always 0. Okay, and that's because of the Merwin-Wagner theorem. To get a superconducting state in the absence of spin-orbit coupling, you really have to break a continuous SO3 symmetry, and you cannot do that. So TC, strictly speaking, is actually 0. But we'll talk about finite systems. Presumably at low temperature, the correlation length would be exponentially long, and we'll imagine that the correlation length is much bigger than the system size. So the system would look superconducting, even though the thermodynamic limit it really wouldn't be. Okay, so that's our phase. That's the phase we're interested in. Okay, now there's an interesting mathematical fact that makes this particular type of superconductor very different from an ordinary S-wave superconductor, singlet superconductor. Okay, and that's this homotopy group, the pi1 of SO3 is actually Z2. Okay, so this means that if you go around the point in such a superconductor and you ask how does the order parameter wind, it can either wind once or not at all. Okay, unlike a usual superconductor where the winding number of the phase can be any integer. So the pi1 of U1 is actually Z. Okay, so this means that the vortices in this kind of system are actually Z2 vortices. So you can have a vortex or not, but there's no anti-vortex. Two vortices can actually continuously be annihilated always. Okay, and this is kind of a fun fact. If you're not familiar with it, it's kind of a nice visual way to understand it. Let me go briefly through that. Okay, so here's how to see it. If you think about SO3, okay, so that's the space of rotations in 3D. You can parameterize such a rotation by the direction and an angle. So that's like a point in a solid ball. Okay, so if you have a point in the ball, the direction is the direction of the rotation axis. The radius is the rotation angle, but you have to identify antipodal points on this on the surface of this ball with radius pi. And that's because a pi rotation around an axis is the same as a minus pi rotation around the same axis. Okay, so antipodal points are identified, and then we're interested in closed loops in this space of SO3. So here's a closed loop. Okay, you can have this red path that goes from the South Pole to the North Pole. So since the South Pole and North Pole are identified, this is actually a closed trajectory. Okay, but then you see that you can, by deforming this path continuously, you can actually deform a path from the South Pole to the North Pole to a path that goes the other way. Okay, and this is like continuously deforming a vortex to an anti-vortex in terms of the order parameter of the triplet superconductor. Okay, so that's an illustration of this fact. Okay, so what we want to do is understand the physical consequences of this special structure of the order parameter space. So to do that, let's write, let's imagine we're deep inside the superconducting state. So we have a fixed magnitude of the order parameter, and the only low energy degrees of freedom are basically the direction of the spin and the phase of the superconducting order parameter, or this SO3 matrix. Okay, so here's a free energy density that you can write in that limit, assuming that there's complete spin rotational invariance. Okay, so these are basically the only two stiffnesses that are allowed by symmetry. So one of them is just the gradient of the D vector, which is a complex vector mod squared, and the other one is the gradient of the magnetization of the Cooper pair, which is D star cross D. This is just D1 cross D2. Okay, and then mod squared. So this is the kappa M term is basically an excess spin stiffness. There's some spin stiffness already included in kappa D. Okay, but these are the only two terms that are allowed by symmetry. Okay, there's a nice way to represent this kind of order parameter. So instead of working with this complex vector D, there's a nice trick. You can actually use a 2x2 unitary matrix in SU2. Okay, so it relates to the D vector in this way. Okay, so this is kind of nice because it encodes the Z2 topology explicitly, because you see that changing U to minus U doesn't change D. That's actually a direct way to see the pi1 of SO3. Okay, now in this representations, you can apply a spin rotation by acting with a SU2 rotation matrix from the left, or you can do a gauge transformation, which is applying this matrix from the right. Okay, so that's all encoded very nicely in this representation. Now, for instance, you can write a state that carries a supercurrent, where the spin direction is completely fixed and the superconducting phase is twisting in space. So that corresponds to a rotation around the z-axis, which changes linearly with x. Okay, so this is a uniform phase gradient, or a uniform supercurrent. Okay, so now because of the fact that the pi1 of SO3 is Z2, if you have two such phase windings, okay, or if a total phase winding of 4 pi, you should be able to continuously deform that state into a state that where the phase doesn't wind at all. Okay, and this is unlike in the usual superconductor. So you know that in a 2D superconductor, if you have a current carrying state, the phase is winding, and the only way to unwind this phase is by creating vortex-anti-vortex pairs that can then dissociate and move to the boundaries of the system, and thereby relaxing the current. Okay, so that process has a big energy barrier because it costs a lot of energy to create vortex and anti-vortex pairs. Okay, basically a logarithmically large energy in the system size. But here, this is not the case. There should be a way to relax the current without crossing any energy barrier. And that's really the special thing about this kind of superconductor. Okay, and Eyal actually found, in terms of this unitary matrix, found this very nice trajectory, explicit trajectory that demonstrates this fact. Okay, so basically, if you take this configuration of the unitary matrix, which is a configuration of the order parameter, which depends on position x, okay, along some axis, and there's a path parameter tau that goes from 0 to 1. So, and this is our order parameter. Okay, so the D1 and D2 are the red and the blue arrows. So you see that at tau equals 0, the phase is just twisting linearly in space. This is a state that carries a supercurrent. And then by twisting the direction of the spin, which is M, that's the D1 cross D2, continuously in space, you can actually get to a final configuration at tau equals 1, where the phase winding is exactly 0. Okay, so it starts from 2 windings and ends up with 0. Okay, so a supercurrent can relax by relaxing the phase winding by 4 pi at a time. Okay, so that's the basic phenomenology, and we'll study consequences of this. Okay, we'll just flash a few consequences, and then maybe I'll conclude. Okay, so first of all, we noticed that for this path to be possible physically, okay, so for this to actually occur, we need some mechanism to dissipate magnetization. So if the magnetization was perfectly conserved, that means if the system was completely isolated, then this cannot occur because basically since if the total magnetization is conserved, we started from a polarized state, and the magnetization just can't change. So this path requires changing, at least in some intermediate state, requires changing the direction of a magnetization. So let's assume the system is coupled to some kind of spin path. This can be either some kind of impurities or just the boundaries of the system. If the system is connected to metallic leads, for instance, there's some way to dissipate magnetization. So that's our assumption. Okay, but once we can do that, there is this kind of a path that allows us to relax the phase twist continuously. And we can ask, is there a free energy barrier in order to relax the supercurrent? Okay, so we imagine if a finite system of length Lx and width Ly, okay, and we have n phase windings across the system is carrying some supercurrent, and we try to deform the order parameter configuration along this path and ask what's the free energy cost. Okay, and so it look like this red curve. There might be some finite free energy barrier, or if the number of windings is big enough, it pays to actually unwind the phase continuously without any free energy barrier. Okay, so you can just insert this expression into the free energy, find the free energy along this path. It's a trial path. This is basically a variational argument. Okay, but what you get is basically there's a critical current density beyond which this energy barrier would go to 0. Okay, so beyond a certain current, there would be no energy barrier at all. You can just smoothly roll down this hill and unwind a 4 pi worth of phase twist. Okay, and this critical current would go inversely with the system size. Okay, so it's really a mesoscopic critical current. That's kind of unusual. Usually in a superconductor you have a finite critical current density. Here it's mesoscopic, and it depends on the ratio between these two stiffness parameters, kappa m and kappa d. And the reason for that is very simple. The more stiff the spin is, the higher the critical current. Okay? It costs more to twist the direction of the spins. Okay, and let me maybe just make two short comments and end. Okay, so first of all, here's a possible experiment that would have interesting consequences as a result of this. This is our triplet superconductor. Okay, suppose we attach leads to it, and we apply a voltage between these two leads. Okay, so this is our setup. The phase would start twisting as usual due to the Josephson relation. Okay, the phase would start twisting linearly in time, and this is what we expect the current as a function of time to look like. Okay, so we apply a certain voltage. So this is basically like the AC Josephson effect. The current would grow linearly in time at first. Okay, but at some point, the current would reach this critical current value where there's no energy barrier to do a continuous relaxation process. Okay, so then what we expect is that the current would actually drop rapidly below the value of the critical current, and then it would start rising linearly again. Okay, now notice that the time it takes to between these events is the time it takes to accumulate a phase of 4 pi, not 2 pi. Okay, so this means that the Josephson frequency, effective AC Josephson frequency you would measure in this kind of setup is actually half the usual Josephson frequency. Okay, instead of EV over H bar, it would be, instead of 2 EV over H bar, which is the usual Josephson frequency in a superconductor, in a Josephson junction, you would get EV over H bar. Okay, and we did a simulation and a model that I won't explain in detail. Okay, there's assuming some Langevin dynamics of the order parameter, where we don't restrict this untwisting path to any particular path. Okay, but we just let the system choose its own path, and this is indeed what we find. Okay, so we find this kind of double Josephson frequency. Moreover, we find that the average current depends on voltage. Okay, so the excess current that you get beyond this value of the critical current, which is determined by the free energy barrier, the vanishing of the free energy barrier, scales like the square root of the voltage. So that's another prediction we can have. Now, okay, if you apply an Inplane Zeeman field, this eventually goes down to usual. This crosses over to usual superconductor, and it does so in an interesting way. Okay, I won't go through the details, but the important conclusion is that in the presence of an Inplane Zeeman field, the critical current density becomes independent of system size, and it grows like the square root of the Inplane of the Zeeman field. Okay, so that's another property of this kind of superconductor. Okay, and I won't go through the third part. Happy if you have any questions on that. There's an interesting experiment by Shachar Ilani here and his wonderful students that I've been involved in the interpretation of, but I won't describe it. So let me just jump to my conclusions. And thank you very much for your attention.
Right, thank you very much, Erez. It was a very interesting talk. So any of your public has questions, please raise your hand or type into the chat box. I don't see any questions. Greg has a question.
Hi, Erez, how are you?
Hi, good.
I guess my question is kind of general. So what do you think is the most interesting new phenomenology of superconductors that arises with these Moire superlattices? Is it the pairing symmetry that you focused on, or are there some other aspects?
Yeah, so right. I mean, yeah, from my point of view, I think the pairing symmetry, turns out to be any kind of unconventional pairing symmetry, and if it's triplet, that would be the most exciting. But I think there's still many open questions about the superconductivity. Is it even at the most basic level? Is it phonons or not phonons? Is it unconventional at all? There are many interesting ideas from Ashvin and Mike Zalaton and collaborators that it's related to Skyrmian physics. So yeah, I mean, I think it's really wide open, the nature of this the superconductor here.
And what about twisted double bilayers? Are you thinking along that direction? Like you get phenomenology by having, 4 layers versus 2.
Yeah. So I mean, so right. So the twisted double layer.
Yeah.
At the end, it's kind of interesting. It turns out the number of degrees of freedom is actually not different. It's still kind of 2 valleys, 2 spins. It's just the band structure is very, very different from the twisted bilayer, and that's what's presumably what's causing it to be different. But yeah, in terms of superconductivity, there's now a debate whether that system is superconducting at all.
I see.
I hope it is. I mean, if it is superconducting, then it really looks like the superconducting state is very clearly very, very close to ferromagnet. So it almost has to be triplet, but it's not clear. I mean, things can be, things can be confusing, and maybe it has misled us to think that this is superconductor. That's still ongoing experiments.
Okay, great, thank you.
Any other question from the audience? Well, I don't see any other questions, so it's time to end. Thank you very much, Erez, for being with us today. It was a very interesting talk. And next week, we will go back with Subir Sachev. So please keep in touch with us and check out our website for our agenda. It was a pleasure to have you all here today. Thank you.